In this video, we're going to see a few more examples of probability problems so that we can strengthen our probability skills, and we'll also learn about a new concept called conditional probability. Let's take a look at this example. Suppose you ask 120 residents of South Hadley if they own a dog, a cat, or both. Of these residents, 62 own dogs, 45 own cats, and 18 own both a cat and a dog. What's the probability a randomly selected resident owns a cat? Well, there are 45 cat owners, there's 120 residents, so the answer is 45 out of 120. Now, what's the probability a randomly selected resident owns a cat and a dog? Well, there are 18 people who own both a cat and a dog, so it's going to be 18 out of 120. Okay, if we randomly select a resident, what's the probability that resident owns a cat or a dog? Notice that we're using the word "or" here. So maybe pause the video and see if you can find the answer. Okay, the answer is, remember that for "or," if we have disjoint events, it's just the probability of the cat plus the probability of the dog. But because these two events are not disjoint, it's possible to have a cat and a dog, then we have to subtract the probability of getting a cat and a dog. So the probability of owning a cat is 45 out of 120. The probability of owning a dog is 62 out of 120. We add those two together, and then we subtract owning a cat and a dog, which we found in the last slide. It was 18 out of 120. And when we add these numbers all together, we get 89 out of 120. And the decimal approximation is about 0.742. So owning a cat and owning a dog are not disjoint events. Okay, what's the probability a randomly selected resident does not own a cat nor a dog? Now notice that this is the opposite of a randomly selected resident having a cat or a dog. Remember, not having a cat nor a dog means they don't have any animals whatsoever, or cats and dogs. And so what we're going to do is find the opposite of this event, which we've already found. The opposite is this 89 over 120, or about 0.742. And if we subtract it from 1, then that will give us the answer to the problem we are trying to solve here. So if I take 1 and subtract 89 out of 120, I'll get 31 over 120, and the decimal approximation is 0.258. All right, here's a new concept. What's the probability if we randomly select a cat owner, what's the probability they also own a dog? So maybe pause the video and see if you can come up with that probability. Okay, so we know that we have a cat owner. There are 45 cat owners. And we want to know, given that we have a cat owner, what is the probability they also own a dog? So the answer here is 18 over 45. Now I have some new notation. This is saying, given, so this line, the line in between dog and cat means given. And it says, what's the probability that the person has a dog given they have a cat? So we're assuming the word in behind the line is what we're assuming. They already have a cat. So given they have a cat, what's the probability they have a dog? Okay, let's reverse this. What's the probability a randomly selected dog owner also owns a cat? Now we're assuming that we have a dog owner. There are 62 dog owners. And the dog owners that also have cats, there's 18 of those. So the probability is 18 over 62. So notice that the word dog is going in the back of that line, and that's because that's the assumption. This is given. Given that we have a dog owner, what's the probability they also own a cat? So this is some new notation. This is called conditional probability. So if you have two events, A and B, in a sample space, and the assumption is the probabilities are greater than zero, the conditional probability of A given B is written like this. You have probability of A with a line. That line means given B. So we're assuming that B is occurring. And how you can find the answer is you just take the intersection, probability of A and B, and divide by the probability of B. And over here in the Venn diagram, and this is just like that problem we were talking about with the cats and dogs. So the thing in the back, let's say the last problem I believe was given that they have a dog. So we're highlighting the event that they have a dog and we're finding the intersection where they have a dog and a cat. So we're putting the dog and the cat on the top and then we're dividing by what's given. And you could switch these as well. You could if you're given A instead of B, if you're given A and you want to find the probability of B, it's still the intersection, the probability of A and B divided by the probability of A. So whatever's in the behind the line, that's what's in the denominator, okay? So you see in the first equation we have given B. So in the denominator of that fraction, it's B, probability of B. In the second equation, we have the line with an A, and on the denominator, we have probability of A. And in both equations, the top is the intersection A and B. So on a test, I won't ask you to memorize these formulas, but I will ask you to know how to use it. So you'll be given this formula, you just need to know what you're supposed to plug in. And we're going to do plenty of examples to help you find the answers. Let's try a new problem. Suppose you roll a die twice. What's the probability you roll a 6 and then a 4? Okay, so this is not conditional probability. I'm just quizzing you here. See if what you remember from the last video and from your homework. So maybe pause the video and see if you can solve this problem. Okay, so what's the probability you roll a 6 and then a 4? Notice that I'm using the word and. So I'm rolling a die twice. I want a 6 and then a 4. So whatever I get on the first roll doesn't influence the second roll. These are independent events. And when we use the word and, we multiply. So getting a 6 on the first roll, if we just focus on that first roll, 1 out of 6. Then if we focus on the second roll, to get a 4 is 1 out of 6. So the probability is 1 over 36. Now, here is an example of conditional probability. Given that you rolled a 6 on the first roll, what's the probability your second roll is a 4? So I'm going to write this using that formula we saw with A and B. This is more of the long way to do it. So this says, given that given that your first roll is a 6, that's the part behind the line, what is the probability your second roll is a 4? So we're going to put the probability of the intersection, that the second roll is a 4 and the first roll is a 6. Well, we already found that in the first problem here. That's 1 out of 36. And then we're going to divide by the part behind the line, the probability that the first roll is a 6. So we're going to take 1 over 36 and divide by 1 over 6. And we get 1 over 6. So that's a little complicated, but because these are independent events, notice that this probability is the same thing as just rolling a 4. That's because the first event does not influence the second event. So when you have independent events, the probability of A given B is just the probability of A. So B wouldn't affect what's going to happen in the second roll. We're going to do some more examples, but before we do that, I need to define a contingency table. So we talked about in the past, if we have data, like here's some data, it's just a little bit of data. I've taken a picture of a spreadsheet, and we've talked about comparing two numerical variables using like a scatter plot, what if we want to compare and learn something about categorical variables? Not just one categorical variable. We learned that we could use bar graphs for that, but what if we want to compare two? We can make something called a contingency table. So for example, I have this data, which is about a brand new test. So some company is trying to, maybe it's a COVID test or something like that, where they have participants and they either have a disease or don't have a disease. Maybe it's COVID or something like that. And what the test, when they took the test, whether they got a positive or negative result. Okay. So let's say I want to compare the test results with whether or not they have the disease, okay? So this is categorical data, and we can't make a scatter plot, but what we can make is something called a contingency table, which is just a table that summarizes all of this data. So what I can do is I can go in and I can ask the computer to count how many times somebody got a positive test and they also had the disease, and how many times somebody got a positive test and didn't have the disease, how many times somebody got a negative test and had the disease, and how many times somebody got the negative test and didn't have the disease. And that could kind of help me understand whether my test is a good test, whether it's the information coming back is reliable. So here I have summed up all of the information from this data set. So you can see on the top, I have disease, no disease, and I have positive test, negative test. So for example, 80 people had a positive test and also had the disease. So that's an intersection here because having a positive test and having the disease, that can happen. And so there's 80 people. So those events are not disjoint. But also, there were people who had a negative test. There's 5 of them that had a negative test and also had the disease. So for 5 people, the test was unreliable there. And you can see the other information here. 4 people had a positive test and no disease. 301 had a negative test and no disease. Now, there's a column that says total and another row that says total. So if we look at the very bottom row, we see 85, 305, 390. So the people who had the disease, 80 plus 5 is 85, and the people who did not have the disease, 4 plus 301 is 305. And then on the other column, where it says the last column all the way to the right, it says positive test. There's 84 people. Um, the number of people who had a negative test is 306. And then if you add those two numbers together, you get 390. So there were 390 people who were part of this experiment or observational study. Okay, so let's focus on that contingency table. So it says a study to see if a new test can detect a disease has the following results. Now, if we randomly select a person from the study, what's the probability that person has the disease? Well, we said there was 390 people, so that's going to go in the denominator, 390. Now let's look for disease. So people who had the disease either received a positive test or a negative test, right? But we have 80 people who got a positive test and had the disease, and 5 who had a negative test and had the disease, but they still had the disease. So total, there's 85 people out of 390. So about 0.218, or there's about a 21.8% chance that a randomly selected person has the disease. Okay, if we randomly select a person from the study, what's the probability that person has a negative test? So negative test is the second row here, and you can see that 306 people had a negative test. So 306 out of 390, that gives us a probability of 0.785. So you could say there's about a 78.5% chance that if we randomly select a person, they'd have a negative test. If we randomly select a person from the study with the disease, what's the probability they have a negative test? Okay, so it is assumed, it is a given that the person we've selected has the disease. So instead of focusing on the 390, we're focusing on the 85. We know they have the disease. Now that we know they have the disease, only 5 people have a negative test. So given that they have the disease, the probability they have a negative test is 5 out of 85, or 0.056. So this is conditional probability. In general, the probability of A given B is not equal to the probability of B given A. So flipping them are not always the same. So if we flip, notice that if we say, what is the random, so the random person from the study, in the past we said, with the disease, what's the probability they have a negative test? If we switch those two, if we randomly select a person from the study with a negative test, what's the probability they have the disease? So we're assuming negative test. And so that means 306 people had a negative test. So we will take the intersection, the people who have the negative test and the disease, that will be 5 out of 306. So in the past, in the last one we switched these, it was 5 out of 85 when it was given that they had the disease, what's the probability they have a negative test. But when we switched them here, it's 5 out of 306. So probability of A given B is not necessarily equal to probability of B given A. Here's another data set. This data set we've seen before is 31 random cherry trees selected from a park. And you can see from the data set that we have whether or not they're below a certain age, below 30 years of age, what part of the park they came from, the east, north, south, or west, the diameter of the trees in inches, and the height of the trees in feet. These cherry trees, when we did a lab where we compared the diameter to the height, and we made a scatter plot and we tried to see if there was an association. Now let's look at this categorical data with the below 30 years of age and the area of the park. Here I've made a contingency table where I've counted how many trees are from each part of the park and whether or not they're above or below a certain age of 30. And you can see that there are a total of 31 trees, just like in the data here. Let's see if we can answer some questions based off this table. So if we randomly select a tree from the sample of 31 trees, what's the probability it's from the west area? Pause the video and see if you can find that probability. Well, there are 9 trees from the west area, and that's 9 out of 31, which is 0.29. If we randomly select a tree from the sample, what's the probability it's from the west or the north area? West and north are disjoint events. You can't have a tree that's both in the west area and the north area, okay? So all we have to do is we have to find the probability it's in the west area and add it to the probability it's in the north area. Remember, the word or means addition. So we just add 9 with 8 and we get 17. So 17 over 31. So the probability is 0.55. If we randomly select a tree from the sample, what's the probability it's from the west and the north area? Now, if we just select one tree, it's impossible to have a tree in the west and the north area. So that probability is 0. These are disjoint events. If we randomly select a tree, what's the probability it's younger than 30 years old? Pause the video and see if you can come up with that probability. Okay, so there are 14 trees that are below 30 years old. So the probability is 14 out of 31, which as a decimal is 0.45. If we randomly select a tree, what's the probability it's younger than 30 and from the east area? So we look in the row of younger than 30 or below 30, and we see where it intersects with east area. There's 4 trees that are both under 30 and in the east, so it's going to be 4 out of 31, or about 0.13. If we randomly select a tree from the sample, what's the probability it's younger than 30 or from the east area? So pause the video and see if you can find that probability. So we're doing an OR problem. Remember, OR is addition, and these two events are not disjoint. We just found the probability of the intersection. We said that the intersection was 4 out of 31. So what we need to do is find the probability it's younger than 30, which is 14 out of 31. We need to find the probability it's from the east area, which is 6 out of 31. And then we subtract the intersection, which is 4 out of 31. And that will give you 0.52. If these were disjoint events, we wouldn't need that 4 out of 31, but because they're not disjoint, we have to subtract it. Otherwise, we would have double counted that 4 out of 31. Given that we randomly select a tree from the north, what's the probability it's older than 30 years old? Pause the video and see if you can find this probability. Okay, here we're not just saying randomly select a tree. If we were randomly selecting a tree, the denominator would be 31. Here we're saying we're selecting a tree from the north. This is a given, the north, and there are 8 trees that are from the north. Now, what's the probability is older than 30? So we know that it's in the north and older than 30. So that's 1 tree out of 8, or 0.13. Let's switch this. Given that we randomly select a tree that's older than 30, what's the probability it's from the north? Pause the video and see if you can find that probability. So the trees that are older than 30, there are 17 of those. 17 trees are older than 30, and there's exactly 1 of those trees is from the north, so it's 1 out of 17, or 0.06. All right, we're almost done. We just have one more topic to cover, and that is, what if we want to find, instead of finding probability of A given B, we want to find the intersection. Maybe we already know the probability of A given B, and the one that we need to find is the probability of A and B. So in this formula, we can solve by multiplying both sides by the probability of B. So if I ask you a question, and you're going to see, especially for events that are not independent, for dependent events. So when we were doing independent events, like drawing 2 cards from a deck, and we did it with replacement. So one event didn't affect the other. Here, when we do dependent events, like taking a card out of the deck, we're going to have to use a new formula, and this is the new formula. So like, given that we took 1 card away, what is the probability of A and B? So you'll see this in some of the examples here. Now, if you have independent events, the probability of A and B is the probability of A times the probability of B. But if they're not independent, the probability of A and B is the probability of A times the probability of B, given that A occurred. So let me go back. You see in red in the top here, the first equation, the probability of A and B is the probability of B times the probability of A given B, or you could say in the second equation, probability of A times the probability of B given that A occurred. We're going to see this in more detail in just a second. I think it'll make more sense when we do some examples. So let's see this. Suppose you draw 2 cards from a 52 card deck without replacement. What's the probability both cards are diamonds? Okay, so what it means without replacement is that I'm going to take a card from the deck, I'm going to look at it, then I'm going to put it off to the side, and then I'm going to draw another card from the deck. Now, I've took a card and put it to the side, so there are less cards in the deck. There's now 51 cards in the deck. So that's going to change the denominator. So let's focus on the first one. So the probability of A and B, we just focus on the first event. We had 52 cards, 13 of them are diamonds. That's the probability of getting that first one. And means multiplication. But I took that card, I took a diamonds card, and I put it off to the side. Now, in this deck, there are 51 cards, and only 12 of them are diamonds. So you can see that it's not going to be like in the past where it was 13 over 52 times 13 over 52. We have to take into account that we put a card off to the side, okay? Now, if you multiply these two fractions together, you get 156 over 2652, which is 0.0588. So there's about a 5.88% chance that this would occur. Let's try another one. I'm going to draw 2 cards from a 52 card deck without replacement. What's the probability the first card is a diamonds and the second card is black? Okay, I'm drawing my card. The first card is a diamonds. I look at it. That's the probability of that happening is 13 out of 52. Now I'm putting that card away. So given that that first card was a diamonds, I want to know the probability the second one is a black card. There are 51 cards left, but I took a diamonds out. That's a red card. So I have 26 black cards left, okay? So it's 13 over 52 times 26 out of 51. If I asked you what's the probability the second card is red, then it would be 25 over 51. But I took a diamonds card. This is asking for a black card, and diamonds are not black. So that's why it's 26 out of 52. 26 out of 51, sorry. So 13 times 26 is 338. 52 times 51 is 2652. There's about a 12.75% chance that this would occur. Let's see if we can do this with 3 cards. Suppose you draw 3 cards from a 52 card deck without replacement. What's the probability all of the cards are diamonds? Pause the video and see if you can figure this out. Just find that you need to multiply 3 things together. And remember, each time you're putting a diamonds off to the side. So pause the video and see if you can get the same answer as I get. Okay, first card, the probability that it is a diamonds is 13 out of 52. I take that diamonds card, I put it off to the side. Now there's 12 diamonds in a 51 card deck. So the probability my second card is a diamonds is 12 out of 51. Put that card off to the side. Now I've taken 2 diamonds cards out. There's 11 left, and there's 50 cards left. So I multiply these 3 things together because I need a diamonds and a diamonds and a diamonds. And means multiplication. So this ends up being 0.0129. Let's try another just to make sure we understand. You're going to draw 3 cards. What's the probability the first 2 are diamonds and the last card is a hearts? Okay, probability the first one is a diamonds, 13 out of 52. Put it off to the side. Now there's 12 cards that are diamonds out of 51. Now you take that card, put it off to the side. The last card is a hearts card. We did not take away any hearts cards. There's still 13 hearts cards, but there's 50 cards left. So if we multiply these 3 fractions together, we get 0.0153. And that's it for this section. I hope it made sense. If you have any questions, you can always email me, and I can try to explain them a little bit better. Please give the homework a try, and you can meet with me over Zoom or during office hours, and we can talk about any of the problems.